Hi, welcome to one more video on feedback amplifiers. So in this video, we will see in detail series shunt feedback amplifier, or it can also be called as voltage series feedback amplifier. So let us consider this is the voltage amplifier. So let us also consider there is a feedback network. So this is the feedback network what I have. And then since I have to sample the voltage, so let us consider there is a load resistor RL. Since I want to sample the voltages will be sampled in shunt. Now you are taking this. Okay, this is now plus minus. We know that has been sampled. You have a voltage source plus minus Vs. So it is now the feedback signal. So now this is Vf, which is plus minus. It is now connected in such a way that you have plus minus here. This is plus minus. This is corresponding to negative feedback amplifier. Okay, negative feedback we have. We know that maybe in the previous courses you might have learned any amplifier for that matter will always have. Of course, so whenever you're representing the amplifier using two-port network, I can represent it having some input impedance R I can write as the input impedance Ri. It will have an output resistance R0 and it will also have an open loop gain A0. Of course, this is Vin, or let me call it as simply Vi. A0 into Vi, this is your A0. So this is the representation of amplifier which has got input impedance of Ri, output impedance of R0, and it has got an open loop gain which is, okay, let me call it as simply A. So this has got an open gain of A. Uh, this is this whatever we are considering an amplifier, voltage gain amplifier. So I will let me rewrite that. So this is my amplifier with input impedance Ri having an open loop gain, because this is a voltage dependent voltage source. So this voltage source depends on the input voltage Vi. It is now plus minus. Its magnitude is A times Vi. And I have got this as R0, and this is my amplifier. This is the amplifier now. I have a load resistance RL connected here. This is my V0. So there is a load resistor RL connected, and of course I will have an input which is Vs that is being applied here. Let me consider an input current of I flowing into the amplifier. So let me consider the feedback network. Let us consider a feedback network which has, let me just type it over here, and just sampling this voltage, connecting it to this. So this is what is sampled here. And let us assume that there is one more dependent source, because I want to know that I want to represent there is some fraction of V0 that is sampled over here. Because what is Vf here? The sampled voltage is some beta times V0. So what is this is beta times V0 is the magnitude of this voltage source. So this is your Vf. It is now coming over here like this. This is the This is the representation of this amplifier which is there in terms of block diagram as much more clear representation of amplifier with some input impedance Ri, output impedance R0, open loop gain of A, and this is a feedback network. We know that feedback network is one which samples the voltage here and then gives the voltage. Here the value of beta is always less than 1. Some fraction of the output voltage is connected back to the input. So how you're connecting it is in this fashion. So that's why this will yield negative feedback. That's why we're going to yield negative feedback. So in this particular combination of a feedback network, let us try to find out what is the values of input resistance, input resistance of the amplifier of the amplifier after feedback. After feedback, it is not only input impedance. Let us also find out what is the input and output impedance or resistance of amplifiers after feedback. We know that for this circuit, without feedback, without feedback, the input impedance is Ri, the output resistance is R0. Now we need to find out after providing the feedback what is the input and output resistance. If you can carefully look at this network, shall I say input input resistance input resistance after feedback as equal to this is what you have after feedback. Shall I write it as Vs by Ii? Because if this is the because you can see when this was the amplifier, so this was input impedance. So we had this as II. So Vi by Ii, is the input impedance, which is Ri. Now, since I have provided the feedback, the input resistance of this entire network is what is Vs by Ii. Vs by Ii. So I need to find out what is Vs by Ii. So this is what is Vs. So can I actually find out what is II here? So can I write II is equal to Vi by Ri? I can write II as equal to Vi by Ri because if this is the current that is flowing into the network, if this is I of I, we know that Vi is equal to II into Ri, so that I can now II is equal to Vi by Ri. So this I can able to write it. Now, using this network, whatever we have, if you apply the KVL to this, can I write minus Vi? This is actually okay, minus Vs plus Vi. This is actually Vf plus Vf is equal to 0. I can write using the KVL to this particular loop. I can write this expression. So finally, can I write it as Vi is equal to Vs minus Vf? I can write it as Vs minus Vf. But what is actually Vf? If you can carefully look at this, Vf is equal to beta times V naught. This is Vf is equal to beta times V naught. But what is V naught? We know that V naught is equal to A times Pi. See here, this is your V naught. Let me just make sure that this is open circuited now. This is open circuited for the time being. Let us consider this as open circuited. So what is the voltage you have here? So this is V naught. Is the voltage is equal to A into Vi? A into Vi. So this is A into Vi. So let us now first consider this as open circuited. I don't have a load resistor RL. So this is A into VI. Now can I write VI as equal to VS minus a. So is it not beta times A into VI? I can write it as so and so. So I can write this entire thing as, so what I do is, this is VI into 1 plus A beta is equal to VI is equal to VI, or sorry, is equal to VS. So can I write now VI, can I write VI as equal to Vs by 1 plus A beta. So here let us substitute this value onto this. We are looking at what is Vs by II, which happens to be the input resistance after feedback. I will write it as RIF. This is, you can see, this is input impedance. F is after feedback. RIF is equal to Vs divided by, in terms of Vi, I will write it as Vs by 1 plus A beta into Ri. Can I just take out this? Will it become, will it become, okay, now this is, will it become Ri into 1 plus A beta? Meaning to say, the input impedance of the amplifier after feedback will become equal to, it is the input impedance of the amplifier without feedback into 1 plus A beta. 1 plus A beta. Meaning, the input impedance of an amplifier will increase by 1 plus A beta compared to the compared to the input impedance that was there before the feedback. Meaning, if Ri is equal to 1K, if 1 plus A beta is equal to 100, after providing a negative feedback of something like this nature, the input impedance after feedback will become 101 kilo ohm. 101 kilo ohm. So there will be an increment in the input impedance of the amplifier if we provide a negative feedback of this nature. So using this, we can able to say that input impedance increases by 1 plus A beta times. The earlier input impedance before feedback was Ri, it will increase to Ri into 1 plus A beta. Similarly, let us see what is, how does the output impedance will change? How does the output impedance will change? Again, let me consider the same. Of course, what is one condition that we have considered here is, while finding the output resistance of the feedback network of the amplifier, we have considered RL as infinity. RL as infinity. So to find the output impedance, so we know that for any given amplifier, how do we find the output resistance? So it has got some gain A. First thing what we do is, first we'll short the input. So Vi will be made equal to 0, and then we will apply a dummy source with amplitude Vx to try to find out what is Ix here. Vx by Ix will become what is Rout. What is Rout? So we should do the same analysis for this type of network also, for this type of amplifier also. So what I'll do is, let me rewrite the same amplifier circuit whatever I had. So this is my Ri, and I have my plus minus A into Vi. This is R naught. This is the amplifier what I have. This is the amplifier what I have, and this is my feedback network having plus minus. This is, sorry, this will go here like this. and I'll have this is a source plus minus Vx. You're trying to find what is Ix here. It goes like this. This is going like this, and then you have this is actually shorted plus minus Vf. Correct? This is beta times V naught. This is beta times V naught. So we have similar type of setup here. This is in general how do we find out the output impedance of an amplifier. We have an amplifier with feedback, so I'm providing this particular source which is having an amplitude of Vx. So Vx by Ix will give me ROF. So what is the output resistance of the amplifier without feedback? It is R0. This is the output resistance of the amplifier with feedback with this combination. So for that, I have to find what is Vx by Ix. Now, can I get the expression for Ix over here? If you can find what is the expression for Ix, can I write Ix as equal to because this is the current that is flowing over here. So can I write that Ix as, so you have a voltage source here, you have one more voltage source here, and you have a resistance. So can I write it as Vx minus 8 times Vi by R naught as the current that is flowing here. This is just you want to find what is Ix. So we assume that there is no current flowing here. So there is no current flowing here because this is open circuit. This is an ideal condition where it will going to simply sample the voltage, no current will go. So here the current is actually zero. Here also current is zero because this is open circuit. So if you write the KVL for this, so can I write Vx as is equal to Ix into R naught plus A into Vi? A into Vi. So from this, can I write Ix as equal to Vx minus A into Vi by R naught? That's what I have written here. That's what I have written. Now the question is, how much is this Vi? How much is this Vi? Is this actually Vi here? Is this actually Vi? Because whatever voltage you have at the input is your Vi. So is Vi is equal to, from this, is Vi is equal to minus Vf here. Can you see this minus is connected to plus and plus is connected to minus here? So shall I say now the input voltage is equal to the negative of the feedback voltage? This is fine here. But what is actually feedback voltage? Is it not beta times V naught? Is it not beta times V naught? Correct? Is this V naught, whatever you are writing V naught, is it not equal to Vx itself? So can I write it as minus beta times Vx as your Vi? So what I do, I will just substitute what is Vi is. So this is Vi is equal to beta times minus beta times Vx. So I can write this expression as Vx minus of A times minus of beta times Vx by R0. So this expression will become Vx plus A beta Vx by R0 is actually Vx. This is actually. So now I can write Ix is equal to Vx multiplied by 1 plus A beta divided by R0. If you rewrite this expression, what is Vx by Ix? Is it not equal to output resistance with feedback? Is it not equal to R naught by 1 plus A beta? Meaning the output resistance of an amplifier which was R naught without feedback will reduce to R naught by 1 plus A beta after feedback. After feedback. So the advantage, because we know that for any voltage amplifiers we need to have the input impedance as high as possible and output resistance should be as small as possible. So we have seen in the input impedance will actually increase by 1 plus a beta times, whereas the output resistance will reduce by 1 plus a beta times. So RIF is equal to RI into 1 plus a beta, and ROF is equal to RO divided by 1 plus a beta. 1 plus a beta. So these are all under ideal conditions. Here with RL is equal to infinity. Here we are assuming that it is not drawing any current. It is not drawing any current. So it is not, let me say it as, it is not loading. What is not loading? The feedback network is not loading your amplifier. So with these ideal conditions, the input impedance and output impedance of the network with feedback will increase and decrease by a quantity 1 plus a beta. This is a very important uh, concept of negative feedback amplifiers. That too in case of uh, voltage series amplifiers with voltage amplification, the input impedance which was Ri will increase to Ri into 1 plus a beta, and for R naught it will be R naught by the feedback resistance will be R naught divided by 1 plus a beta. Okay, in the next video we will see what is the impact of this type of negative feedback if we consider a practical consideration. So these are all under ideal condition that okay, R is equal to infinity and you don't have any loading effect. So in the next video, we'll see if there is a practical consideration of you have some RL and you have some loading effect. In such case, how does this amplifier will behave and how do we find out what is input impedance, output impedance, and all those stuff.